Good evening. Time to start section 6 and proving theorems about perpendicular lines. If you've made it this far, I guess it's probably time to give you a joke. What does an acorn say when it grows up? Geometry! Alright, it would be funnier if somebody was here to laugh. But anyway, section 6 is all about the proofs again. So again, we're trying to show something is true. There's about 5 new theorems here, but only 2 have names. The first 3, you need to know them, but you're not going to ever really use them. You will, however, use the 2 with names. You need to memorize, sink those ones into the memory with their name attached. So you will learn how to prove statements about parallel and perpendicular lines, really emphasizing the perpendicular lines here. The first one is theorem 3.8, no name, but it says if 2 lines intersect to form a linear pair of congruent angles, then the lines are perpendicular. So if I see something like this, linear pair, 2 angles forming a straight line, and they are both congruent angles, well then I know that this line is perpendicular. Theorem 3.9 says if 2 lines are perpendicular, then they intersect to form 4 right angles. You might use this one actually. However, when you use it, you say perpendicular lines intersect to form 4 right angles. You'll actually just say out the theorem. You probably won't use theorem 3.9. So this is what the picture would look like. If it's a right angle here, all 4 of these angles are perpendicular, are right angles. Theorem 3.10 says if 2 sides of 2 adjacent angles are perpendicular. So if I look here, angle 1 and angle 2 are adjacent. They share this ray and this vertex. And I know that this is perpendicular. Then I know that the angles have to be complementary. In this case, angle 1 and angle 2 are complementary. The last 2 theorems both have names. Perpendicular transversal theorem. This one you might use more often than the others. It has a name. You probably will. If a transversal is perpendicular to one of 2 parallel lines, then it is perpendicular to the other 2. Sorry, the other also. So, in this case, if I have a picture like this, these 2 lines here are parallel, and this transversal is perpendicular to this one. If I think of what that means, and I go back to these corresponding angles postulate, well, that tells me because the lines are parallel, then this angle and this angle here both have to be congruent. If they're both congruent, they have the same measure. If they have the same measure, they're both 90 degrees. If they're both 90 degrees, they're both right angles. And if this angle right here, is a right angle, that means it's perpendicular. So these 2 parallel lines are perpendicular to this transversal by this theorem. So if I see this, I then can say this because of this theorem. The last one, the last new theorem. Lines perpendicular to a transversal theorem. In a plane, if 2 lines are perpendicular to the same line, then they are parallel to each other. I said that there was no transitive property for perpendicular lines, and that makes sense. If I look here, these 2 lines are both perpendicular to this one, which means, well, this is first of all my transversal. This angle and this angle here are both consecutive interior. 90 plus 90 is 180. So I have consecutive interior angles being supplementary. It forces these 2 outside lines to become parallel. Yes, if you have 2 lines being perpendicular to the same line, they are parallel to each other. I'll say that again. If 2 lines are perpendicular to the same line, then they are parallel to each other. You need to know it. It makes sense too. You can prove this one also as a theorem. Alright, the last thing that we need to talk about is not a theorem, but it's this ideal, the distance from a line. For instance, if I was going to say how far away I was from Chicago, yeah, I could take the road map and take all the roads there. But I'm not going to take a roundabout way of how far am I away from Chicago. I'm going to go to Montana first and then come back to Chicago. No, that's not the distance from here to Chicago. The distance from here to Chicago is the shortest possible distance. In that case, it's always going to be this perpendicular distance. Any other length is not going to be the shortest distance to the line. It's like as if I say, wherever you're sitting, walk to the wall. You're going to walk at an angle that's perpendicular to the wall. If you walk at an angle that's parallel to the wall, you'll never reach it. Makes sense. So in this case, if I was trying to find the distance between this point and this line segment right here, then what I would do is I would find the length of this line segment because it's the one perpendicular. The shortest distance, or the distance from a point to a line, or between two lines, is always the perpendicular segment from those 2 points. So if I was trying to find the distance between these two parallel lines here, I would look at this segment here because it's the perpendicular distance between the two. That's it. That's it for vocabulary. So at this point, you should be able to prove statements about parallel and perpendicular lines. I know we didn't go over any proofs, but there will be a few in the examples. And you should be able to determine what the distance from a point to a line is. Yes, you should be able to tell me how far it is. Use the distance formula from section 3 of chapter 1. And if you don't know which video that is, I believe it's the 3rd video of unit 1. Till next time.